Okay, so in this video, we're going to go over an example of a related rates problem. And one of the most common related rates problems that I found when I was a student in calculus was a ladder problem. So the process for any kind of related rates question is exactly the same if we can follow these 6 steps. And it can be a little bit daunting in the beginning to go through all of these parts, but that's why I'm doing this video. I'm here to do it with you, so hopefully we can do it together. So I'm going to start by reading a question that you can find in your related rates worksheet. A ladder 10 meters long rests on a horizontal ground and leans against a vertical wall. The foot of the ladder is pulled away from the wall at the rate of 0.5 meters per second. How fast is the top sliding down the wall when the foot of the ladder is 5 meters from the wall? So the first step for again, any related rates question is to draw a picture. So over here, I've drawn the picture where I have my ladder, and then I also have to assign variables. In this case, I'm going to have x represent the distance from the bottom of the ladder to the wall. Let x represent the distance from the bottom of the ladder to the wall. And I'm also going to let y represent the distance from the top of the ladder to the ground. Got ahead of myself, from the top now. In the event that any students are thinking that these first 2 steps, drawing a picture and assigning our variables, are trivial, I'm going to say that it's extremely helpful if you're ever checking in with another student's work. There's no guarantee that you're using the same variables or even drawing the same picture. So being able to see what the other person is writing as well as assigning your variables is going to be really useful if you're ever looking at another person's work. So I would say that we've done the first step so far as well as the second. And the third step is stating what we know and what we don't know. So I always like to draw a little table. I have knowns and unknowns. And in the problem I read, we were told that the bottom of the ladder was moving away from the wall at a rate of 0.5 meters per second. So this tells me that we are given dx dt, and that it's equal to 0.5 meters per second. And the question was asking us, when the bottom of the ladder is 5 meters away, what is the rate at which the top of the ladder is moving towards the ground? So in this problem, we're going to be we need to find dy dt at the precise moment that x is equal to 5 meters. Okay, so we've listed our knowns and unknowns. The fourth step is we have to find a way to relate what we know and what we don't know. And the way we will start is actually by relating x and y. So if I'm looking at this picture, I see a right triangle. One of the first equations I'll think to myself about how x and y are related is the Pythagorean theorem. So I can write x squared plus y squared is equal to z squared, but in this case my hypotenuse, I know my ladder is 10 meters long, so I'll just write is equal to 10. Now, the reason why finding this equation is helpful is because in order to use what I know, which is the derivative of x with respect to t, and to find the derivative of y with respect to t, I can use implicit differentiation and take the derivative with respect to t on both sides. So fifth step is I'm going to take the derivative with respect to t of both sides. So I have x squared plus y squared over here, and then I have 10 over here. Now, I know that the derivative of a constant number is just going to be 0, so my right side will turn into 0. And in order for me to take the derivative, on the left side I'm going to have to use implicit differentiation and rewrite the derivative with respect to t as, for the first term I have the derivative with respect to x of x squared times dx dt. Now, recall that I know that this is equivalent to the previous expression because I could cancel out these dx's and be left with d over dt. And again, this was a sum, so that means I'm also taking the derivative of, with respect to t of y squared, and I'm going to rewrite this as d over dy of y squared times dy dt. One thing that I just noticed is, since we're using the Pythagorean theorem, x squared plus y squared equals z squared, my ladder may be 10 meters long, but because I'm using the Pythagorean theorem, this should actually be a 100. The good news is even though we're taking the derivative with respect to t, the fact that this is 10 versus 100, it will still give us a 0 on the right side. So let's continue, assuming that I remembered the Pythagorean theorem correctly. There should be a 10 squared right here. And then, now that I have rewritten d of dt as d over dx and then d over dy, I can take the derivative, and I'll have 2x times dx dt, and then plus 2y dy dt equals 0. Now, the goal is to solve for dy dt when x is equal to 5 meters. So I want to solve for dy dt, so that means I'm going to put everything that I don't want onto the other side. In this case, I'm going to have 2y times dy dt equal to negative 2x dx dt. And then I'm going to divide both sides by 2y. So I can write divide by 2y, divide by 2y, and I should be left with dy dt is equal to negative x over y dx dt. So at this point, all I have to do is, this is the general derivative function dy dt. I have to just find the answer specifically when x is equal to 5 meters. So I'm going to carve out a little space right here so I can complete step 6, which is when x is equal to 5, I have to figure out not only what x is, I have to also know what number to plug in for y. So I have my little triangle right here, and I say, okay, well, when x is equal to 5, then y is equal to the square root of 10 squared minus 5 squared. This is 100 minus 25, which is 75. So this would be the same as the square root of 75. And I could simplify this by pulling out the square root of 25. This is the same as 5 root 3. So I know that y is equal to 5 root 3. I know x is equal to 5. And I also know that dx dt is equal to 0.5 meters per second. So now that I'm plugging in all of my pieces, I have dy dt is equivalent to negative 5 over 5 root 3 times 1/2 meters per second. And if I doing my arithmetic correctly, I should get dy over dt is equal to, these 5s can cancel out, so I should have negative 1 over 2 root 3 meters per second. So I didn't really talk about how I knew what the unit was for this question, but if I think of, in general, like the fact that the two sides of my wall, the ground and the wall, are measured in terms of meters, if I want to figure out the rate at which the ladder is sliding down with respect to time, it makes sense that my unit would be meters per second. So I know you've just completed all 6 steps to a related rates question, but because I want to develop good habits, I'm really going to encourage you to write one conclusion sentence in words, relating all of the math we just did to the actual context of the problem. So we know that dy dt is equal to negative 1 over 2 root 3 meters per second, but in terms of the problem, I can say at x equals 5, the top of the ladder is sliding down the wall, at a rate of negative 1 over 2 root 3 meters per second. So there you have it, our first related rates problem. I hope this helps as you do more and more word problems using implicit differentiation.